This section is probably what we've been building up to for some time now. We can actually get to and define the dimension of a vector space. So let me start with the following. Suppose B equals B1 up to Bn is a basis for a vector space B. Then we've seen that V is isomorphic to Rn. That little symbol that I used there just means isomorphic. That means it is just like Rn in the way it behaves. Remember, in R squared, the standard basis looks like the following. 1, 0, 0, 1. Now, in polynomials of degree less than or equal to 1, a standard basis is this, 1 comma t. But I sort of indicated to you that you could think of them as the one I can think of as 1 plus 0 times t, and the other one I could think of as 0 plus 1 times t. So what I do is I think of the first polynomial to be just like the vector 1, 0, and the second polynomial to be just like the vector 0, 1. In R3, the standard basis looks like the following. 1, 0, 0, comma, 0, 1, 0, comma, 0, 0, 1. Now, in P2, we have the following as a basis, 1 comma t squared. And I do exactly the same thing. The 1 I think of as 1, 0, 0. The t I think of as 0, 1, 0. And the t squared I think of as 0, 0, 1. Why? Well, 1 is the same as 1 plus 0 times t plus 0 times t squared. So what I'm doing here is 1 is in the first slot, there's a 0 in the second slot, and a 0 in the third slot, or if you will, coordinate. Let's use that term. Now take a look at t. T is the same as 0 plus 1 times t plus 0 times t squared. Once again, the first coordinate is 0, the second coordinate is 1, and the third coordinate is 0. And the same with t squared. That is going to be 0 plus 0t plus 0t, well, actually 1t squared. So this is what we're talking about here. I have in P2, I have exactly 3 vectors that will do all the work that I need to. In R3, I have exactly 3 vectors that will do all the work that I need. Same thing with in R2, 2 vectors are all that I need. And in P1, I need exactly 2 vectors to do everything I need. So when you're in R2, any set of more than 2 vectors will be linearly dependent. I'm not talking about the zero vector here, so let's keep that in mind. I'm talking, so I should say any set of non-zero vectors. they will be linearly dependent. Any set of vectors with less than 2 vectors will not span. Similar things happen for R3. In R3, any set with more than 3 vectors will be linearly dependent. Any set with less than 3 vectors will not span. So this is what we're going for. In R2, we need exactly 2 vectors. Any more, too many. Any less, too few. In R3, we need 3 vectors. Any more, too many. Any less, too few. So that's basically the gist of what we're getting to. And through the theorems and stuff like that, we're going to prove that not only is it true for R3, but for any vector space of with a certain basis. So let me do a theorem to start things off. If B equals B1 up to Bn is a basis for a vector space V, then any set of more than n vectors will be linearly dependent. Proof. Let U1 up to U sub P be a subset of V where specifically the number P is greater than N. Alright, what I'm going to do then is write each of the U vectors in terms of the B vectors. So U1, I could do C1, B1 plus C2, B2 up to CN, BN. And then for U2, I could use, well, let's do D, D1, B1 plus D2, B2 plus dot, 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 plus GN, BN dot, 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 U sub P will equal, well, there's an issue right here. I'm running out of letters to use. I got E, F, G. I don't know exactly where P goes to, so I don't exactly know what letter to use for this. So I'm going to have to come up with a better scheme for listing these coefficients than I have been, because this is simply not going to cut it. I don't know how to describe a general U thing. So let's get rid of this, and I'm going to try this again. Here's what I'm going to try. Instead, I'm going to let U1 be equal to C1, 1, B1 plus C, let's say 2, 1, B2. So what I'm going to do is these are just constants, the C11, C21, but I'm going to allow myself a couple of indices here so that one of these indices is going to agree with the vector. So see how this first one agrees with that one, this first two agrees with that two, and the second part of the index will be from which vector it came from. So by the time I get to the nth one, I got Cn1 times Bn, like so. Then this allows me to come up with a convenient way of labeling U2. This time, all of my second indices will be a 2, but the first ones will go from 1 to n. So I'll have C12 B1 plus C22 B2 plus dot 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 plus Cn2 Bn. And so I'll just do one more so you get the feel for it. U3, then this one will be C13 B1 plus C23 B2 plus dot 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 plus Cn3 Bn. And now you can see it's working. So let me go ahead and finish this off. What will then UN look like? So I will have C1n B1 plus C1n B2 plus dot 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 plus n B2 plus Cnn Bn. Now what I'm going to do then is I'm going to look at U1, but its B representation. The coordinate mapping is what I'm going to look for. What makes that up? Well, I have C11, C21 up to Cn11. So it goes C11, C21, and that goes to Cn1. For the second one then, my coefficients are C12, C22, all the way up to Cn2. And on up till UN B, and that one was C1n, C2n, until I got to CNN. Now, as usual, form the matrix with those columns. In particular, I want the UI B's as columns. So what we get is a big old matrix. We have C11, C21 up to Cn1. Then we have C12, C22 up to Cn2. And then finally, where we end at the last one, we have C1n, C2n up to Cnn. Now, notice that the U's go more than up to n, they go all the way to p. That means, what am I going to do? I'm going to, if I run out of, if I go past n, then I might have, let me write it in here, I'll have C1 n plus 1, and then I'll have C2n plus 1, all the way down to Cn times n plus 1. And I'll keep going until I get to P. C1P, C2P, CNP. So what do we have? We have n rows, p columns. Now recall, we can have at most n linearly independent columns. Remember that from the work that we did earlier. If you try to go and get this into an echelon form, you'll get your 1, 1, 2, 2 all the way down to nn, but then you'll have other vectors that are still existing that you weren't allowed to whittle down through the echelon process. So since we can have at most n linearly independent columns, the columns are linearly dependent. Consider, let's see, we have 1, 2, 3, 4, 5, 6, which is in R2. Now, according to what we just did here, we can only have 2 linearly independent columns. So let me make the matrix out of those 1, 2, 3, 4, 5, 6, and do my elementary row operations until I've reached as close to the full form echelon that I want. So the first thing I'm going to do is take negative 2r1 plus r2. So the first row will not be affected, but the second row will. Negative 6 plus 4 will be negative 2, and negative 10 plus 6 will be negative 4. Now I'm going to divide the second row by 1/2, or by 2, 1/2 R2. So 1, 3, 5, 0, negative 1, negative 2. And then I'm going to take 3R2 plus R1. Well, from here, hopefully you can see that I could have stopped here actually, because you can see from right here, you have 2 pivot columns. But here is even the more echelon form. And what I was talking about, if you tried to clean up in the theorem all those vectors, you would have been left with p minus n columns still that you wouldn't have been able to do this with. So here you only have 2 pivot columns. So only 2 linearly independent vectors in the set. And remember, if you were to list a basis for these column vectors, remember you'd want to take the first 2 vectors in there, because they're the ones that you know for a fact are linearly independent, because they have this reduced echelon form of a diagonal matrix. In the previous example, so what I'm going to do in the previous example, let A be the matrix of those columns. And suppose we solve the augmented matrix A with 0. So that means we would have ended up with 1, 0, 0, negative 1, negative 1, negative 2, 0, 0. Well, if we convert this to equations, what do we have? X would be equal to z, and y would equal negative 2z. So this solves this. That means that our null space for the matrix A will be the span of a single vector. The best way to do it, I'm going to write these x, y, and z. Well, if I let z be equal to 1, then y will equal negative 2, and x will also equal 1. So there's the null space for A, and this makes sense. We know that the number of columns minus the dimension, if you will, or the number of vectors in this basis for null A will equal the number of linearly independent columns. And we knew that. We knew we had 2 linearly independent columns. We knew that null A had to be have only one spanning vector anyways. But notice this. Let's take, go back to the original matrix. We know this. 1, 2, 3, 4, 5, 6 times any vector from the null space. We'll zero this thing out. Let me see. We have 2 by 3, 3 by 1, so we have a 2 by 1. But more importantly, if you were to multiply this out, you can get the following. 1 times the vector, 1, 2, there's my 1, minus 2 times the vector, 3, 4, plus 1 times the vector, 5, 6, will equal the 0 vector. Just to convince you that's true, let's take a look at our numbers. Well, look, the first coordinate will be 1 minus 6 plus 5, that is indeed 0. And then we have 2 minus 8, that's negative 6, plus 6 equals 0. But you can see that the 1, 2, negative 1 shows up right here in the coefficients. Consider (1 plus 2t), 3 plus 4t, 5 plus 6t, which is a subset of P1. And as I mentioned, I'm going to make the matrix A just like I did before. But remember, you can think of this. If we take, if for example, this here is a B basis, then what we can do is think of this here becoming the vector 1, 2. Similarly, this here, this second polynomial, can be thought of as the vector 3, 4, and this last one can be thought of as the vector 5, 6. So I'm using that isomorphism stuff. But we already know that null A was equal to the span of 1, negative 2, 1. Well then, if you take 1 times 1 plus 2t minus 2 times 3 plus 4t plus 1 times 5 plus 6t, you'll end up with the 0 vector, just like I did before. Let's just make sure. 1 minus 6 plus 5 does 0 out that part, the constant part 0. Then for the stuff attached to t, I'll have 2 minus 8 will be negative 6 plus 6. So you can see, and then we also know, while we're at it, I don't know if you'd call it a column. We know that the column of A was equal to 1, 2, 3, 4. So this implies that P1 is the span of 1 plus 2t and 3 plus 4t. If V is a vector space, with a basis of n vectors, then every basis for V has exactly n vectors. So for the proof of this, let C be a basis with m vectors and let B be a basis with n vectors. So I have two bases potentially with a different number of vectors in each basis. So since C is a basis with m vectors, any set with more than m vectors is linearly dependent. Well, this means, so therefore, n cannot be more than m because, well, that basis with the n vectors is linearly independent. So according to an earlier theorem that we had last section, this means that n cannot be more than m. In other words, we have n is less than or equal to m. But now you can play the same game on the other side. Since B, well, capital B, since B is a basis with n vectors, any set with more than n vectors is linearly dependent. This forces m to be less than or equal to n, same exact thing. Well, whenever you have a situation like this where m is less than or equal to m and m is less than or equal to n, you have no choice but to determine that m is equal to n. So any two bases have exactly n vectors. Oh, this here, any set with more than m vectors is linearly dependent. That was the theorem that we just proved, not from last section. So I don't know why I said that, but that was from the first theorem that we did today. That's what this comes from. So what you have now is, no matter what, if you have two bases, they have to have the same number of vectors in them. So this allows us to define the dimension of a vector space. So I'll put stars because this is big. Call it a definition. Let V be a vector space that has a basis with n vectors. Define the dimension of V to be n. In symbols, we use this notation, DIMV equals n. Here's a couple of notes that we want to make. Note, if the dimension of V equals some number n, we call V finite dimensional. There are such things as infinite dimensional vector spaces, like the set of all polynomials where you have no limit to how high the powers of t can go. That's an infinite dimensional vector space. We don't do much with them. Maybe we'll use them as an example here and there, but we don't really study them that much. A couple other things you might want to know. The dimension of r to the n, as you didn't know, is n. The dimension of p sub n minus 1 is n. That's why things like r3 is isomorphic to p sub 2. It's all because it has that constant term, so the powers of t don't keep up with all the coefficients. We also do this. This is a definition because 0 is sort of outside the lines of anything. We don't even say, I guess you'd call this the zero-dimensional vector space. It just, even though it has a vector in it, it's the zero vector. So this is just a definition. Keep that in mind as it will be used throughout the course. Not very important, but it will be necessary to recognize it sometimes. Now, let me do an example to illustrate some things. Find a basis and the dimension for the following set. Let me see, we have 4 rows. It looks like 3a plus 6b minus c. Then we have 6a minus 2b minus 2c. We have negative 9a plus 5b plus 3c. And then we have negative 3a plus b plus c. And this is where a, b, and c are real numbers. So I want to find a basis and the dimension for that. Well, if you remember, we could rewrite this in the following format. I could write this, well, let me organize it a little bit here. I think I'll do this way, 3a, 6a, negative 9a, and negative 3a plus, so I'm just going to break that vector up into 3 vectors, 6b, the sum of 3 vectors that is, minus 2b, 5b, and b, plus, and the same goes with the c's, negative c, negative 2c, 3c, and c. A, B, and C are real numbers. And then I can factor out the A from the first one. 3, 6, negative 9, negative 3. Plus, then I can pull a B out from the second one. 6, negative 2, 5, 1. And then C times negative 1, negative 2, 3, 1. Let me keep going here. If you'll recall, this equals the span of the following vectors. 3, 6, negative 9, negative 3, comma, 6, negative 2, 5, 1, comma, negative 1, negative 2, 3, 1. So its dimension will be either 1, 2, or 3. It's not going to be 0 because, well, it's not. We don't just have the 0 vector. We don't have the 0 vector listed here. So what do we do to figure this out? Well, you've done this a million times by now. We make ourselves a matrix with those vectors as columns. And this is just like determining the column space. Really, there's our columns right here. We're going to work this until we figure out how many linearly independent columns we have, and then we'll know how many vectors are in our basis. So the first thing I'm going to do is starting with this entry here, I'm going to wipe out the items below it. So I'm going to do negative 2r1 plus r2. So it'll put a 0 underneath of that. Let's see. So I have negative 14 here. And then I'll have 2. I'll wipe out. There'll be a 0 there. Good, that's nice. Then I wanted to use this 3 to wipe out this negative 9. So I'll do 3r1 plus r3. So it will give me a 0 there. Then I'll have 18 plus 5. That'll give me a 23 in this spot. And then, oh, look at this. I can wipe out another item there. Good. Finally, let me just take R1 and add it to R4. I automatically looked over here to see. And then when I do R1 plus R4, I'm going to do 6 plus 1 will be 7. Well, you can stop right there. You can see that you're going to have a pivot column here and a pivot column here. Now I could use, if I want to, say this negative 14. Let me do it just to show you what I'm talking about here. I am going to divide the second row by 14. Now, if I take 6r2 plus r1, I'll wipe out the entry above it. If I take 23r2 plus r3, I'll wipe out this entry. And if I take 7r2 plus r4, I'll wipe out that entry. So I'll just put a big squiggle here so you know how I get it. I mentioned all that. Now there's no question, you can see we have 2 pivot columns. That means that the dimension of the column space, so the dimension, did I give the name of this matrix? I did not give this matrix a name. So I am going to call this matrix by the name A. So dim call A is equal to 2. And that means that my basis is given by 3, 6, negative 9, negative 3. And 6, negative 2, 5, 1. Don't forget that to use the original items from the matrix and not the whittled down version. We're going to let V equal the span of the following polynomials. 3 plus 6t minus 9t squared minus 3t cubed 6 minus 2t plus 5t squared plus t cubed, comma, negative 1 minus 2t plus 3t squared plus t cubed. And this, of course, is in p sub 3. So I want to do the same thing. Find a basis for b. So with that in mind, I'm going to do the same thing I did before. 3 plus 6t minus 9t squared minus 3t cubed. I'm going to think of it as the following vector. 3, 6, negative 9, negative 3. Hopefully you can follow right here. 3, 6, negative 9, negative 3. Same thing for the next one. 6, negative 2t plus 5t squared plus t cubed. I'm going to think of as the vector 6, negative 2, 5, 1. And the last one in my set, negative 1 minus 2t plus 3t squared plus t cubed, I'm going to think of as negative 1 minus 2, 3, and 1. And as you might have guessed, I'm going to make up a matrix with these vectors as my columns. And as you know, this was the previous example, so let me just grab its final matrix that I went through all the effort of doing. I think I will take this guy right here. So then, as before, we have two pivot columns. There they are. That means that I should use the first two polynomials as my basis. So a basis for v is, let me see, we had 3 plus 6t minus 9t squared minus 3t cubed, comma, 6 minus 2t plus 5t squared plus t cubed. And the dimension of v was equal to 2. I don't know if I said it on the previous example, but that dimension was obviously 2 as well. Next, I want to compute dim column A and dim null A for the following matrix. A equals (3, 4, negative 6, 10). Well, once again, we'll just take 2r1 plus r2. We get 3, 0, 4, 18. You don't have to go any farther than what I have now. I now know that column of A is spanned by both columns, since I have two pivot columns. So both of these columns must be useful in the span. So that means then for, well, let me do this. Dim col A equals 2. Then remember, dim null A equals the number of columns, which is 2. So 2 columns minus the number of items in its span, minus 2 spanning vectors. Really, you're just going to do 2 minus 2 will equal 0. So once I know that null A equals just the 0 vector. We're operating in R2 here. And so dim null A equals 0. A little more robust example, but the same idea. Let's compute dim call A and dim null A for this very large matrix. Let me see, it's a 4 by 6. So I have 1, 0, 0, 0, 3, 0, 0, 0, negative 4, 1, 0, 0, 2, negative 3, 1, 0, negative 1, 7, 4, 0, and 6, 0, negative 3, 0. So you can see it's already got some pivot columns in place. Right here, column 1 is a pivot column. And this is not a pivot column because the first non-zero entry, well, should be right in that spot, and it's not. Here we have a pivot column because of this 1. This is a pivot column. And likewise, since we drop down 1 and there's a 1 as the first non-zero entry in this row, there's another pivot column. And then I do not have any more pivot columns. So dim call A equals 3, and dim null A would normally be, well, I would say it would, the column A, by the way, is limited to 4 as the biggest it could have been anyways. But now that we know it, we take the number of columns, which is a total of 6. So the number of columns minus the dim call A, and that equals 3. Determine a basis for null A in the previous example. So let me start with the original matrix, whittle it down as much as I need to whittle it down to get the answers that I want. We already know that the dimension is going to be 3, but I want to show it quite clearly. So what we're going to be looking for is to take the original matrix. We had 1, 0, 0, 0, 3, 0, 0, 0, negative 4, 1, 0, 0, 2, negative 3, 1, 0, negative 1, 7, 4, 0, 6, 0, negative 3, 0, and make it into an augmented matrix. So it's like we're trying to see which vectors get mapped to the 0 vector. So let's see what I can do here. What I can try to do, I want to try to solve this for them. So the easiest thing to do is, this is sort of in echelon form, but I can get it row reduced if I use these pivots to wipe out the entries above them. So I'll be working column 3 and column 4. So what I'll do is I'll take 4R2 plus R1. So that won't affect the first 2 columns in this matrix. But here it'll wipe out the entry above it. The entries below it will not be affected. In fact, its own entries won't be affected, and neither will the items below it. And let's see what happened to the rest of the stuff in the first row. So I took 4 times this row plus this row. So 4 times -3 is -12, plus 2 will give me a -10. 4 times 7 will be 28, minus 1 will be 27. And then, well, I didn't affect this because there was a 0 in the second row. Now, I'm going to go and use this one right here, to wipe out the entries above it. So I will do 3R3 plus R2, and I will also do 10R3 plus R1. Of course, the first 3 columns are unaffected by this. The fourth column, I've zeroed out the items above. The item below will be unchanged. And since I was working only the rows above, let me put my zeros all in. And I can put zeros over here. That will be unaffected no matter what happens. Now let's see what happened to these entries over here. So I took 3 times 4, which is 12, plus 7, that'll give me a 19 into that spot. And then 3 times -3 will be -9, plus the 0, put a -9 into that spot. And then I did 10 R3 plus R1, so 40 plus 27 will be 67. And then -30 plus 6 will be -24. Now, what we said before still stands. I have a pivot in column 1, I have a pivot in column 3, and I have a pivot in column 4. We know the dimension of the null space is 3. Now watch what happens here when I change these. I'm going to use x1, x2, x3, x4, x5, and x6. So the first row is x1 plus 3x2 plus, I don't have an x3 and x4, but I have an x5, 67x5 minus 24x6. That's going to equal 0. Then the next one, the next row, I have an x3 plus 19x5 minus 9x6, and that will equal 0. In the third row, I have x4 plus 4x5 minus 3x6 is equal to 0. And so let me go ahead and solve these. You can see here, I'm going to solve x1 will equal -3x2 minus 67x5 plus 24x6. x2, you don't see x2 anywhere else in here, so x2 will just equal itself. That's going to be free. So there's one of 3 dimensional pieces. Next, x3 will equal -19x5 plus 9x6. x4 will equal -4x5 plus 3x6. And then I don't have x5 anywhere else, so x5 will equal itself. That'll be free. x6, the same thing. And so the null space will look like this. We go ahead and make one big vector of -3x2 minus 67x5 plus 24x6. x2. I need, excuse me, I need 6 rows for the null space. x2, of course, was x2. x3 was negative 19x5 plus 9x6. Then we have x4 was negative 4x5 plus 3x6. Then x5 and x6 were free. I'll leave this sort of as an exercise to you to show that it equals this span, although I have done it several times. We have, when you think of the x2 vectors, I have a negative 3, I have a 1, but then zeros for the rest. So one of the vectors will be that. Moving on, if you look, then I have x5s and x6s. Look at the x5s. I got a negative 67. I have a 0, negative 19, negative 4, 1, and then 0. Let me put those in. So I had negative 67, 0, negative 19, negative 4, 1, and then 0. And then finally the x6s, I had a 24, then a 0, then a 9, then a 3, 0, 1. So you can see that the dimension of null A, we already knew this, but I wanted to specifically list the vectors that gave that was the basis for null A. Prove that the Laguerre polynomials span P3. What are those, you might ask? Well, here they are, the following. We have 1, then we have 1 minus t. It's a set of 4 polynomials. 2 minus 4t plus t squared. 6 minus 18t plus 9t squared minus t cubed. So from this, I'll form columns. If you think of the 1, I'll see if I can make this underneath of the items in there. So for 1, this is like 1, 0, 0, 0. For 1 minus t, this is like 1, negative 1, 0, 0. For 2 minus 4t plus t squared, I'll have 2, negative 4, 1, 0. And then finally, for this last polynomial, I'll have 6, negative 18, 9, and negative 1. Well, not much to do here. You can see from this that we have 4 pivot columns. So the dimension of the column space, let's call it A, just to give it a name, equals 4. Not only this does it span, but this is an invertible matrix. It not only spans, but they're linearly independent. So this means the columns span. I'll put quotes around that, P3, because the columns are these things. They're not these, but they are just like them. So the columns span P3, and they are linearly independent. So they form a basis. let T from V into W be a linear transformation obviously where V and W are vector spaces. Suppose H is a subspace of V. Then the image of H under the transformation T is a subspace of W. So to prove this, first start with the zero vector. Is 0 in this? So we're going to let T of the zero vector in B, we proved this a while back ago, is equal to the zero vector in W. So the zero vector in W is in the image of H. So as we map H there, the zero vector gets mapped to the zero vector here. That proves we have 0 in there. Now 2, I need to show that, let's suppose T of V and T of U are in T of H. Then T of V plus T of U equals, according to the rules of linear transformations, that equals this. Well, immediately that is in, see, V plus H is in H. So this item here is in T of H. Let me help you out a little bit here. T of H equals all of the images of the vectors in H. So that's the definition of it. So all I got to do is show that the item was mapped by T and these vectors. By saying this right here, I'm saying that V was in H and U was in H. That's why this thing and this thing are in T of H. So together, when I add them together here, this item, V plus U, is in H. We know that because H is a vector space. Then T of that is in T of H. So we'll do the same thing that we did before. Let's look at C times T of U. Of course, C is a real number, U is in H. Then according to our rules, I can write this as T times C of U, which immediately means that it is in T of H. So therefore, T of H is a subspace of W. Now, if V and W are finite dimensional, we immediately see that T, well, better than that, that the dimension of T of H is less than or equal to the dimension of W, simply because T of H is a subspace of W. We're going to let H equal the span of, say, M vectors, since it's finite dimensional. T of H equals the span of T of H1, comma T of H2, comma dot 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 T of H and M. Now, it's possible that one or more of these vectors is going to be 0. It's possible that that can happen. Well, we know that T maps 0 to 0. There could be things like, for instance, there could be items that are in the null space of this thing that's more than just the 0 vector. So some of these could be 0. So what I'm getting at is that the dimension of T of H is less than or equal to M, because one or more of these things could be 0. Prove that H equals the set of all x, y, 0 such that x and y are in R is a subspace of R2. Well, this shouldn't be too bad. Let me write this solution. Notice that H does equal the span of the following vectors: 1, 0, 0, 0, 1, 0, and I should have said this is a subspace of R3. Now, then we can see that it is generated by two vectors, so that immediately means that H is a subspace. By the way, if you wanted to know what it looked like here, what exactly is H? It's basically, H is kind of like R squared, but it's embedded in R3. This is like along the x-axis, and this is along the y-axis. So what we have here, if you want to see what H looks like, if you're interested in its physical look, since the third coordinate is 0, then the first vector in there only goes up to 1, but it's like this. And then the next vector is like this, and it ends at 1 for y. And since they're allowed to stretch or go negative or anything like that, then what you're going to end up getting is a plane here. And it essentially goes right through the origin. So what this is the XY plane is exactly what that is in there. And it's just like R2, as you can imagine. You've seen this if you took Calc 3 especially. R2 is really the plane, this plane is really R2, sort of embedded in R3. It's not exactly, it's not a subset, but a copy of it is embedded inside of R3. Any two-dimensional subspace in R3 must be a plane, hence the two-dimensional. So it's spanned by two vectors. It must be a plane that passes through the origin. Well, that's just because the 0 vector has to be in it. That means the space must have the 0 vector in it. It must go through, well, 0, 0, 0. So seeing as that's in there, that means that the space must pass through that particular vector and there hence contain it. A couple of theorems to end things out, although they're not exactly little bitty theorems, but they're important. Let's start with let H be a subspace of a finite dimensional vector space V. Any linearly independent set in H can be extended to a basis for H. Also, the dimension of H is less than or equal to the dimension of V. I think I made use of that in one of the previous examples, but that's okay. Let's start, first of all, with the simple case. If H is simply the zero vector, then the dimension of H is equal to 0, and that's obviously less than or equal to V. V can't be less than 0. So from now on, we're going to assume that H is not simply the zero vector. Let, I guess we'll call it S, equal H1 up to H sub k be a linearly independent subset of H. Now, if S does not span H, then there is a vector H in H with well, then for what we've seen before, since it's not a linear combination of these vectors, this implies that the set H1 up to HK, and I can add in that H, is still linearly independent. And if I need to, I can add more vectors H. So if this new set does not span H, add more vectors until it does. I mean, you can only go up so far until you reach the full dimension of H itself. So this process has got to stop. Eventually, you're going to get as many vectors as the dimension of H is. So let's assume that H is equal to the span of H1 up to H sub k, but then I added in more vectors, let's say up to H sub p, like this. So the dimension of H is equal to p. Well, clearly that's going to be less than or equal to the dimension of n, since all of those H vectors are also in V. So we can play the same game. The set H1 up to HP is a linearly independent set in V. So we can add more vectors if needed until we get a basis for V. Notice I said we can add more vectors if we need to. That means that V, the dimension of V, has to be at least P. Otherwise, if it were less than P, this says we have to be able to extend it to a basis for V. Well, then the dimension of V can't be less than this. Otherwise, you can't extend this in any way, shape, or form. So just because of that, we know that the dimension of H has got to be less than or equal to the dimension of V. And one thing I should mention is whenever you see a theorem with a name, it's important. This theorem is called the basis theorem. So suppose V is a vector space and the dimension of V is equal to n, where n is greater than or equal to 1. Obviously, the zero space doesn't really do anything. Then we have two results. One, any set with n linearly independent vectors in V is a basis for V. 2, any set of n vectors in V that span V is a basis for V. Proof. Most of this is not so big and hard to prove. It's just a matter of being formal about all the stuff that we did. Let's start with the first one, and let's let S equal V1 up to Vn be a set of n linearly independent vectors in V. Then we can extend S to a basis for V by adding in linearly independent vectors. But if we do that, then the dimension of the extended set will be greater than n. So S must be a basis itself. The second one, suppose U equals U1 up to UN spans V. According to the spanning set theorem, I'll tell you what that is in a minute. There is a subset U, let's call it U swiggle of U, that is a basis for V. If you remove a vector from U, to get U squiggle, then V will still equal the span of U squiggle, but the dimension of U squiggle is less than or equal to n minus 1. That obviously cannot happen. And the spanning set theorem, I've already talked about it. It's basically what we just said there. If we have a spanning set, then some subset of it will still span but be linearly independent. That's what the spanning set theorem says, and so we get this result.